Welcome back. Now I'm here in GameplayEffectTypes.cpp taking a look at the fGameplayEffect context NetSerialize function, which takes 3 inputs. Now, boutSuccess is probably the most self-explanatory. It returns true if serialization was a success. Let's keep working from right to left and take a look at PackageMap, the uPackageMap class. If we right-click and go to Declaration or Usages, we see that it's a U object, and it says maps objects and names to and from indices for network communication. So this is just a tool used to help map objects to indices. Why? Because when serializing, all the objects, all the variables of a struct are converted into strings of zeros and ones. And you can think of this as a bit array, an array of bits, zeros and ones. And when you serialize a whole bunch of things next to each other, it helps to know what's the index for when one object starts and another begins. So uPackageMap is used for that. Now, the leftmost or first input parameter is the farchive called AR. Now, let's take a look at the farchive. We'll go to Declaration or Usages, and the comment says base class for archives that can be used for loading, saving, and garbage collecting in a byte order neutral way. Byte order neutral is kind of networking lingo for the way that the bytes are handled in a word. A word is a unit of data that contains bytes, and byte order neutral is sometimes referred to as big endian, endian with an E, not with an I, and it's just a way that bytes are ordered in each word or each fundamental unit of data for a processor. Now, it doesn't really matter. We don't have to know too deeply how that works. We just have to know that farchive is capable of storing serialized data, and it also has the ability to serialize things. Notice it has the operator left shift overloaded for lots of types. When you see this operator with an operator here and parentheses, this is an operator overload. And this right here says that we can use the left shift operator with an farchive on the left-hand side and an ftext on the right-hand side. And look, the comment says serializes an ftext value from or into an archive. Now, there are lots of these for lots of different types. So the farchive is capable of serializing lots of different types. But the key words I want you to see that I don't want you to overlook are from or into. Now, that's kind of interesting. From or into seems to imply that we can take an ftext and use the left shift operator and serialize it into the archive, or we can take that ftext and the archive can take the serialized data and unserialize it and store it in that ftext. So the left shift operator, yes, it looks like it's pointed to the left, but think of it as both ways. It works to and from the archive. Let's talk about this. So we know that there's this archive struct, and its type is farchive. And we know that it's good for saving, loading, and storing data. Now, it stores this data serialized as a series of bits. And it overloads this left shift operator for lots of different types. And we know that it works both ways, depending on the context, if we're saving or loading. And that's exactly how it works. If we have an farchive and we're using the left shift operator, and on the right-hand side we have some Boolean variable, for example, well, if we're saving, then that left shift operator is going to take that Boolean value and serialize it and store it in the archive. However, on the other hand, if the context is different, if we're in the process of loading, then we're going in the reverse direction. That series of bits is deserialized and then stored in that Boolean that exists on the right-hand side of the left shift operator. So just be aware of the versatility of the farchive's overloads for this operator. So now that we know about that, let's go back to gameplay effect types. And I'd actually like to go back to the CPP file gameplayEffectTypes.cpp because we need to understand what's going on here. We know about the input parameters and what they do for us, but now let's talk about the logistics of how this happens. Now the first line here is a uint8 declaration, a local variable called repbits. And this unsigned 8-bit integer is set to 0. Now we have an if statement taking the AR, this F archive, and checking to see if it's saving. So the archive seems to know if we're saving or loading data. And if we're saving, it performs some kind of check, some validation, checking the member variables. It's checking B replicate instigator and instigator.is valid. What it's doing is trying to decide, should we serialize that instigator? If the answer is yes, then that means we want that instigator in our gameplay effect context struct to be replicated whenever this struct gets replicated. Now, if instigator is not valid, well then why bother serializing it, right? So that's why we're checking. But what is this business here? Repbits, pipe symbol, equal sign, 1, left shift, 0. How do you even read this? Well, it's read as repbits, bitwise OR equals 1 left shift 0. In order to understand this line, we have to kind of break it down piece by piece. So let's analyze this a little closer. We know that NetSerialize is creating a local variable called repbits, and repbits is an unsigned 8-bit integer. What that means is in binary, this is all zeros with 8 binary digits, 8 bits. A uint8 is 1 byte, which is 8 bits in size, and we're initializing it to 0, so all 8 bits are 0 in this variable. Now, the line that we're confused about is this one, repbits, bitwise OR equals 1 left shift 0. Now, bitwise OR equals is just like plus equals or times equals. It's equivalent to taking repbits and setting it equal to itself, bitwise OR 1 left shift 0. So these two lines are equivalent. Now, this here is the bitwise OR. It's half of the OR symbol that we're all familiar with. And this is the left shift or shift left operator. So what exactly are these operators doing? Well, I'd like to take a look at the bitwise OR just by itself. Let's say we have a variable called O. It's a uint8, and let's say that its value is 0, which means in binary, it's 8 bits, 8 digits, all of which are 0. Now let's say we have another integer called 1. This is also a uint8, and in binary, this is what it looks like. 8 digits, all zeros except for the rightmost digit, which is a 1. Now let's say we'd like to perform a bitwise operation on it, the bitwise OR. So how does the bitwise OR work? Well, the result is an unsigned 8-bit integer, 8 digits long, and each digit is the result of an OR of 1 bit in one of the integers and 1 bit in the other integer. So let's take the leftmost digit in each one. We perform an OR. Now, how does an OR work with Booleans? If both the left and right-hand side are false, then the result is false. If either one of them is true, then the result is true. That's how ORs work. Well, they work the same with ones and zeros as well. If both digits are zeros, then the result is a 0. That means for the next digit over in each one, we compare them, they're both 0, and that means the result is 0. The same goes for the rest of these. We have all zeros, so for the rest of those digits in the result, we get 0. The only place where they're different is this very rightmost digit in each of these integers. In O, it's a 0, and in 1, it's a 1. Now, 0, bitwise OR 1 is going to result in 1. If either one of them are a 1, the result is a 1. So if they're both 0, the result is a 0. So the result of a bitwise OR of O and 1 is this. All zeros with a 1 at the end. That's just the number 1. Now that was a pretty easy example. Let's try another one. Let's say that O is this number here. We have a 1 in a digit that's 2 away from the end at the left there. And we have 1, which is this number. Now, the bitwise OR results in a uint 8, and we check bitwise each digit, performing the OR. Now, these pairs of digits are all zeros, so that means there's 0 in the result. And these pairs of digits all have at least a 1 in one or the other of the two variables, and that means that the results for these digits are all 1s. So the result of the bitwise OR of these two numbers is this number. So now that we know about the bitwise OR, the thing we need to talk about next is the shift left operator. Now, when used like this, with an integer to the left and an integer to the right, we need to think about the result in terms of bits. Now, in most modern compilers, integers are 32 bits. But we're going to treat these like they're 8-bit integers just for simplicity's sake for now. So the left-hand side of the left shift operator is 1. If it were an unsigned 8-bit integer, it would be this value. Now, what this expression 1 left shift 0 means is to shift all the digits to the left by 0. In other words, don't shift them at all. So that's pretty easy. Let's take another example. 1 left shift 1. Now again, assuming that these integers are 8-bit, we would take the left side of the shift left operator, which is this number, and we shift left by 1. Now, that means we shift all the digits to the left by 1. And so this 1 here is going to end up 1 digit over, and any digits coming in from the right-hand side will be 0. So the 1 at the very end will be replaced by a 0, and the digit next to it will now be a 1. Now, what about this digit all the way over here to the left? It's getting pushed out. We completely lose that. So if it was a 1, it would be gone, and whatever was to the right of that endmost digit is now going to replace it. So 1 left shift 1 is going to result in this value. All zeros, but that 1 has shifted over. Now all those other zeros to the left of the 1 have shifted over as well. So if they were 1s instead, those would also be shifted over, so keep that in mind. Let's do another simple example, 1 left shift 2. Here's 1, and we need to shift all the digits to the left by 2. So the 1 all the way there at the right is going to shift over once and twice. And those 2 zeros all the way at the end are going to be pushed out and they'll be lost. So the result of this is this value here. That is how left shift works. And just to drive the point home, let's try 1 left shift 3. Here's 1, and we have to shift to the left by 3, which means the 1 will travel 1, 2, 3 digits over. These 3 digits at the end will be lost, and the result will be this number. Now, rep bits is a uint 8, but it doesn't have to be. Let's say, for example's sake, that we create one in our NetSerialize that's a uint 32. That would be 32 bits. And if we initialize it to 0, it would be all zeros. Here's what the bits would look like. Now, if we take rep bits and we use, say, this operation on it, rep bits bitwise OR equals 1 left shift 0, that would be equivalent to taking rep bits and setting it equal to itself, bitwise OR, the expression 1 left shift 0. Let's see what result we would get from this. Here is 1 left shift 0. As we've seen, 1 left shift 0 is going to take the value 1 and shift all the digits to the left by 0. In other words, it's just 1. So since we know 1 left shift 0, we can take rep bits, which starts off at 0, do a bitwise OR with 1 left shift 0, which we know is 1, and the result is going to be rep bits. Here's all the zeros, bitwise OR, and here's 1 left shift 0, which is just 1. What do we get when we take the bitwise OR of these two numbers? Well, we get 1, as all the digits are 0, except for that 1 at the very right, and the bitwise OR between 0 and 1 gives us 1, so the result is 1. Okay, simple example. But the thing is, rep bits has changed. It started off with all zeros, and now it has a 1 right there at the end. So this expression that we've done, this rep bits bitwise OR equals 1 left shift 0, has changed rep bits in a way, and we refer to that change as flipping that bit at the end there. Now, if we count bits from right to left, and the very first digit there we consider to be the 0th digit, then we say we flipped the 0th bit. Now, after we flipped the 0th bit on rep bits, we know that its value is now equal to this, all zeros with a 1 at the end. Now let's say we take rep bits and do this again, only we use 1 left shift 1 this time. How does this work? Well, we know that 1 left shift 1 is this value. It's the value 1, but all the digits have been shifted to the left by 1 digit. So it's now no longer just 1, it's this number. So if we were to take rep bits and do the bitwise OR with 1 left shift 1, we would have rep bits, which is 1, OR, and then 1 left shift 1, which is this value. Now, what's the result of the bitwise OR between these two? Well, it would be this. All the digits are 0, except one of the numbers has a 1 at the end, and the other has a 1 right there, 1 away from the end. So the result is a bunch of zeros with 2 1s at the end. In other words, we've flipped the first bit, if we're counting from right to left, starting at 0. So 1 left shift 1 is going to flip the first bit. And notice that we kept the bit all the way at the end there. Rep bits started off with that bit set to 1, all the others were 0, but this line has now flipped that second bit. So they're both 1. Now let's say that we take our 32-bit int rep bits, and we've already flipped the 2 endmost bits on it. And let's say that we take rep bits and we do this operation on it. Rep bits bitwise OR equals 1 left shift 2. What does this do? Well, what is 1 left shift 2? It's this number. It's the number 1 with the 1 digit shifted over by 2. So it's right there, 2 away from the end. And if we want to calculate rep bits or 1 left shift 2, then we would take rep bits, which is now this number, or, and then we would take 1 left shift 2, which is this number. Now, what's the result of the bitwise OR? Well, here it is. We took rep bits, which had 2 1s at the end, and we flipped the second bit. Now it has 3 1s at the end. So we're starting to see a pattern here. Now let's go back into the code and find out just what this means for us. We're only doing this if the archive is in saving mode. So look at what each of these if statements is checking. First, we saw that it's checking if the instigator is valid and if we should replicate the instigator. If B replicate instigator is true, if those are both true, then we flip that 0th bit. And rep bits has all zeros, but it now has actually a 1 at the rightmost digit. This is a very compact way of storing a bunch of Boolean values, basically. We're designating the instigator to be represented by the rightmost digit in this rep bits bit array. The effect causer just happens to be represented by the next one because we're checking to see if it's valid and if we should replicate it, and if so, we flip that next bit on rep bits. We then check the ability CDO variable. If that's valid, we flip the next bit. So assuming these are all valid, then rep bits is changing by having its zeros replaced by 1s in each subsequent bit going from right to left. And if one of these fails, say source object is not valid, for example, then we will not flip that bit, and then we'll continue. If actors.num is not greater than 0, we don't flip that 4th bit, right? So by the end of this 8-bit integer has zeros and 1s that represent whether or not we should replicate or whether or not we should serialize these variables. Now after that, AR calls serialize bits, and it takes rep bits, passes that in. It actually passes it in by address. This is the address of operator, and then it receives the length in bits. Now let's count these. We have 1, 2, 3, 4, 5, 6, 7 times that we've flipped bits. So serialize bits wants to know if we've used all those bits or not. We didn't. We only flipped 7 of them. That last bit wasn't used. So we're telling serialized bits we only care about the first 7. And serialized bits is going to do some really cryptic looking serialization by taking those 7 bits, however many we pass in here, and serializing those into the archive. So it's going to know, it's going to remember in the archive. The archive is just a string of bits, and it's going to remember that these 7 bits are representative of whether or not we should serialize these variables. Now after that, look at this. We're checking rep bits now. We're doing something else with rep bits that looks probably equally confusing. Now keep in mind this first set of bit flipping steps here is done inside the if check if AR is saving. But after that, this stuff is in no such if check. So all of this only happens if saving, but all of this happens regardless of saving or not. And remember, this operator works both ways. If we're saving, we're going from right to left, and we're serializing what's on the right into the archive. But if we're not saving, then it goes from left to right. Whatever is serialized becomes deserialized and stuck right into the variable on the right. Now, the question is, what are these conditionals doing, right? This might make you sort of scratch your head a bit. So let's talk about this part now. We have rep bits, and then this is the bitwise AND, similar to the bitwise OR, only it's the AND version. And then we have some left shifting going on. This first one is rep bits, bitwise AND, 1 left shift, 0. So let's analyze this one. So in these if statements, we have rep bits. Now in this example, let's just say it's a uint32. We know it's a uint8, but it doesn't really matter. Continuing with our example though, let's say that rep bits is this number, right? We've already flipped the first 3 bits. Now, in our if statement, we're checking if rep bits, bitwise AND, 1 left shift 0. So let's look at this one piece at a time. 1 left shift 0, we know that that's this number. So what is this rep bits, bitwise AND, 1 left shift 0? Well, rep bits is this number. Bitwise AND, this number, which is 1 left shift 0. What does this produce? Well, with a bitwise AND, it's just like a bitwise OR. It's happened bitwise, bit by bit, comparing 1 digit on one variable with 1 digit on the other. And if they're both 0, the result is a 0. If only one of them is a 0, the result is a 0, just like an AND. True and false returns false. The only way we'd get a 1 is if both digits are 1s. That's only that rightmost digit there. So rep bits and 1 left shift 0 is this value. Now, this is all inside of an if statement, isn't it? Let's take a look at this again. Here it is. So we know that in our hypothetical situation, if this all evaluated to a bunch of zeros with a 1 at the end, well, that's just a 1, and it's a non-zero value. And if statements consider any non-zero value to be true. It considers only 0 values to be false. So in our hypothetical situation, we would make it inside this if statement. Now, what's the significance of that? The significance is that the result of this operation gives us true because that first digit, which we called the 0th digit, is 1. We interpret that as the first variable represented by that digit has been serialized or should be serialized. Both are the case. In the case where we're saving, it should be serialized. We're going right to left. In the case where we're loading, it has been serialized and needs to go from left to right. So basically, if we're checking rep bits versus 1 left shift 0 with a bitwise AND, we know that 1 left shift 0 is all zeros but a 1 on the 0th digit, the rightmost digit. If rep bits has a 1 there, we'll make it inside this. If rep bits has a 0 there, we will not. In other words, if we flipped that bit up here because we know that the instigator should be replicated, then we'll make it inside here. If we never flipped that bit because instigator was not valid, for example, then we don't need to get inside here and archive the instigator or unarchive it. Make sense? And the same goes for the rest of these. We're checking rep bits against 1 left shift 1. That's all zeros except a 1 just next to the end digit. There's a 0 at the end and a 1 next to it, right? If rep bits has a 1 there, that means we flipped it up here. And we did that because we wanted to replicate effect causer. We wanted to serialize it because it was valid, right? If it was valid, that bit will be a 1. We'll make it inside here, and we'll get to serialize or unserialize. So you catch the drift. And the archive overloads the left shift operator for lots of types, but not all of them. Notice that for the array here, we can't just use the array with the left shift. We have to use other means. There's this function NetSerialize array, which will serialize the array. We also see that the hit result had to be handled a little differently. In the case that the archive is loading, there's a check here to see if the hit result is not valid. If it's not, then a new fHit result T shared pointer is created and stored in the hit result shared pointer member variable. And then the hit result itself has a NetSerialize function designed to serialize hit results. So that's how you serialize hit results. NetSerialize TArray _ default is a way to serialize T arrays. So as you can see, there are a couple of exceptions to this left shift business. And way down here at the bottom, notice there's a check to see if the archive is loading, and if so, we call add instigator. Well, we know what this does, and the comment is telling us why. It says just to initialize instigator ability system component, because we know that that gets set along with the instigator and the effect causer as well. So this function does the courtesy of calling add instigator, and then it just sets b out success equal to true, and it returns true. So all of that is just NetSerialize for the gameplay effect context. Pretty crazy, right? And we need to do this in our custom effect context. And not only do we need to take care of all these, but we also want to handle serializing our new 2 Boolean variables. And we're going to do it just like it's done here in NetSerialize. So what do you think? Are you up to a challenge? Would you like to do this on your own? Or would you like to follow along with me? You're going to get that choice in the next video. And I'll see you soon.